Hello and welcome to the second part of Visualizing Gravity. In this section we'll be visualizing Einstein's gravity. So we're going to be no longer looking at vectors pointing in certain directions. We'll be looking at the curvature of space. So to simplify this, I could use the Schwarzschild solution, which is basically assuming that the mass is spherically symmetrical, so the space curvature around it is spherically symmetrical. The two functions I use to create these diagrams are the Schwarzschild radius and Flamm's paraboloid, which is here. The arguments for the Schwarzschild radius are gravitational constant, the mass, and speed of light. And the functions for Flamm's paraboloid are the distance, which I've called r, from the center of mass. Here it is in one dimension. This is basically, it's just a representation because it's impossible to visualize curvature in one dimension. So by adding a fictional dimension, we can see how the lengths and such can be represented. There's various scalars which change the curvature. And because it's spherically symmetrical, we can extend this concept to two-dimensional curvature just by rotating this two-dimensional line around the z-axis. This has the same kind of scalars. You can just change these. And notice that it has no argument for the radius of the spherical mass. So it's equivalent to Shell's theorem in Newton's gravity. So regardless of what the volume of this kind of spherical mass is, it will always create the same curvature outside of its body. So it could be a black hole or Jupiter or some huge sun. If it has the same mass, it will create the same curvature outside of the body. Okay, that concludes this visualizing gravity section.